Hello, my name is Elizabeth Guidry. Welcome to the Think JSOU series presented by the Office of Strategic Engagement at the Joint Special Operations University. We're happy to welcome our distinguished speaker today. This video is unclassed and will be recorded and posted to the JSOU network. Please keep in mind that the views and opinions of the speakers are their own and may not necessarily reflect the views, opinions, and policies of the United States government, the United States Department of Defense, the United States Special Operations Command, or the Joint Special Operations University. If you have any questions after the video, please contact us at thinkjsou@jsou.edu.
Greetings, everyone. Welcome to this Think JSOU entitled Sea Level Rise and Overwash Effects, Accelerated Climate Security Implications for the U.S. and our island nation partners. I'm your moderator, Peter Cloutier, Professor of Development and Human Security at Joint Special Operations University. We have a fantastic team of presenters today who are going to talk about the subject. Before jumping into their presentation, let me give you the following description as a preview, taken almost word for word from one of their earlier publications. Sea levels are rising with the highest rates in the tropics, where thousands of low-lying coral atoll islands are located. Most studies on the resilience of these islands to sea level rise have projected that they will experience minimal inundation impacts until at least the end of the 21st century. However, these have not taken into account the additional hazard of wave-driven overwash or its impact on freshwater availability. This team that you're about to hear studied the impact of sea level rise and wave-driven flooding on atoll infrastructure and freshwater availability under a variety of climate change scenarios. They have shown that the nonlinear interactions between sea level rise and wave dynamics over reefs will lead to what they call annual wave-driven overwash of most atoll islands by the mid-21st century. Note, this analysis has been based on current greenhouse gas emission rates. This annual flooding will result in the islands becoming uninhabitable because of frequent damage to infrastructure and the inability of their freshwater aquifers to recover between overwash events. This team research provides critical information for understanding the timing and magnitude of climate change impacts on atoll islands that will result in significant, unavoidable geopolitical issues if it becomes necessary to abandon and relocate low-lying island states. I'll add my own 2 cents here. We understand climate change to be global. We understand frequencies and intensities of related events or episodes to magnify over time. Yet what I find so compelling with this team's research and its findings is that climate security must be maintained by new forms of partnership, as our traditional parameters of conflict, even competition, are no longer sufficient for thinking of solutions that only answer part of the equation, and often for not long enough when so. A brief disclaimer, I want to add that components of this body of work, referred to by RC 2334, were funded by the Department of Defense Strategic Environmental Research and Development Program, or SERDIP, the U.S. Geological Survey Coastal and Marine Geology Program, and Deltair Strategic Research, with support by the U.S. Army Garrison Kwajalein Atoll. We have quite a team to present the latest to you in reference to what I just summarized, but before we begin, let me offer a quick introduction to you. First, Dr. Curt Storlazzi is the research geologist and oceanographer at the USGS Coastal and Marine Hazards and Resources Program and a research associate at the University of California at Santa Cruz Institute for Marine Science. 2 of his prominent research areas are, 1, the influence of physical processes on coral reef ecosystems, and 2, the influence of climate change and sea level rise on coral reef-lined coasts. He's authored, co-authored, or contributed to 184 scientific publications. By my count, apologies if it's more. Dr. Storlazzi was honored by the U.S. Coral Reef Task Force with the Scientific Achievement Award presented by Department of the Interior Assistant Secretary Cantor on September 2nd, 2022. The award was voted on by representatives from 12 federal agencies, 2 states, and 5 territories. It is only the 4th time in the past decade that this recognition has been awarded. Dr. Patrick Barnard has been a coastal geologist with the USGS Pacific Coastal and Marine Sciences Center in Santa Cruz since 2003 and is the director of the Climate Impacts and Coastal Processes team. His research focuses on storm and climate-related changes to the beaches and estuaries bordering the Pacific Ocean. His research has been published in over 80 peer-reviewed scientific papers, including Nature, and presented over 100 times at scientific conferences and universities. Ms. Andrea O'Neill is an oceanographer also with the USGS Pacific Coastal and Marine Sciences Center. Following 11 years of meteorological and oceanographic forecasting in the Western Pacific, she now works on future coastal flooding hazards projections using the Coastal Storm Modeling or COSMOS system, applying her expertise in coastal and marine hazards projections, hydrodynamic simulations, coastal impacts with climate change, and team building. Well, from that long opening, Dr. Storlazzi, let me turn the presentation over to you.
Well, thank you very much, Peter, and the Joint Special Operations University. So Peter gave a very nice introduction on some work we did again for the Department of Defense's Strategic Environmental Research and Development Program on Kwajalein Atoll. This is part of a much larger project that Patrick runs, along with Andy, who's one of our lead modelers on that. I'm also listing Maya Hayden, our communications and engagement lead, who's not here today, but should be a point of contact for moving forward. But the work we did was part of the USGS Coastal Storm Modeling System, or what we call COSMOS, and it's an effort to provide consistent national projections of future coastal flooding due to climate change and sea level rise to evaluate risk and to guide prioritization for adaptation. So today we're going to provide first a shared understanding of what data we're producing with COSMOS, when it will be available and where. That'll include kind of the background or underlying science and a modeling overview, kind of a peek under the hood of this large modeling system. And then the application of COSMOS, how it can support DoD planning for coastal climate change, also Department of State, Department of Interior, our international colleagues. And discuss, hopefully, in the engagement afterwards, some of the potential applications and opportunities for collaboration. And if there's time, hopefully, some of the discussion, we understand the relevant DoD timing and status and scale of climate adaptation planning so that we can better deliver the necessary information to help you address your science needs. So we know the Department of Defense is already dealing with coastal hazards. There's impact to operations, infrastructure, contaminants, freshwater availability, threatened endangered species, and cultural resources you see here kind of across the Atlantic and Pacific basins. But we know sea level's rising and the rate is accelerating. We have a plot here of time on the x-axis and sea level on the y-axis. And we've seen that over the past few decades that the rate of sea level rise is increasing. And so there is an acceleration. And we know that more is on the way. We're seeing here a figure from the Sea Level Rise Interagency Task Force. There's sea level rise scenarios. So there's and so again, on the x-axis is time, y-axis is the meters relative to 2000 sea level. So they provided these 4 different sea level rise scenarios, basically driven by greenhouse gases or increasing the atmospheric temperature, the oceanic temperature that's causing thermal expansion, melting land ice, and driving this sea level rise. So what we want to do is to be able to provide science to help guide management actions of climate change and sea level rise. And so to do that, we've developed a number of storm return period projections for the annual storm, the 20-year storm, the 100-year storm. And we did this at management scale resolution. So at about 10-meter resolution for a series of sea level rise scenarios from current up through 3 meters of sea level rise, which is clearly a far end projection, but if there's very sensitive infrastructure, at least it provides kind of a high end scenario. And using robust, consistent, and accurate methodology. Now, these scenarios, sea level rise scenarios, line up with the Interagency Sea Level Rise Task Force, which the Department of Defense is a member. And we did these because these scenarios are kind of timeless. We can adapt them to the various planning horizons and guiding information. For example, there's the Intergovernmental Panel on Climate Changes, AR5 report, and those values change to the AR6 report, or the US National Climate Assessment, or academic literature such as the COP et al. Series. And those keep changing that say, by 2100, we think it's going to be 67 centimeters. We thought that in the 2017 publication, the 2023 publication, maybe it's going to be 84 centimeters. So instead of kind of chasing those, we provided these kind of timeless sea level rise scenarios. And so what we can do is fit any of those projections to these current set of scenarios. So it's, again, this modeling system and the results are intended to help plan for sea level rise when it matters most, and that's during storms and extreme events. Again, here we have a plot through time along the x-axis. The y-axis is meters relative to sea level, and you see those interagency sea level rise task force scenarios again, and where our suite of Cosmos scenarios fit to those. So, like, for example, the Cosmos 2-meter scenario could be the high scenario as close as 2100, or the intermediate high scenario almost out at like 2030. So again, providing they're timeless. As those projections change, they can just be fit to those horizons.
All right, thanks, Curt. To start off with a quick overview of the methods, our approach uses an explicit high-resolution simulation of waves, currents, storm surge, and all the relevant physics that leads to the resulting coastal flooding. So this really helps capture the dynamic impacts of these storm events in an explicitly mapped format. This isn't a proxy, this isn't an approximation, it's really an explicit mapping. It also considers the future evolution of the storm patterns using the global climate models for the coming century. So this isn't using historical observations or historical records, but really is a reflection of what we expect to see in the next century. Because those global climate models are usually at a fairly coarse scale, we use state-of-the-art techniques to really scale down those changes at a global scale down to local impacts, and are able to use those scaled down winds and waves to drive these simulations. All of our model framework is extensively tested, calibrated, and validated with local historic data for test simulations. And these flood projections are based on dynamic wave setup. So compared to some other methodologies that may use maybe a total water level setup or run up, using the dynamic wave setup really helps show the impact of what truly gets flooded versus what gets wet. And so as Curt had mentioned, all of these scenarios are available for a range of sea level rise scenarios, really provides a flexible suite of projections for any planning horizon, as Curt had mentioned, but it also allows for different levels of risk tolerance and also allows you to stay up to date with the latest science. So as our scientific understanding evolves on how much sea level rise we expect to see, for a certain time period or time horizon, there's going to be a scenario that fits that need. And our methodologies are consistent across regions, so it really provides a consistent suite of projects or products along lots of coastline that allows kind of a common operational picture for the risk coming in the next century. Okay, so from that unique methodology, we have a suite of core products that are generated and served on the web and also available for download for more technical needs. As Curt said, these are run for a whole range of sea level rise scenarios, from current sea level all the way to 3 meters worth of sea level rise. And it's for a whole range of storm scenarios or storm conditions, from an annual storm to a 100-year coastal storm. And that yields kind of a really robust library of different sea level rise and storm conditions to fit many planning needs. And so with each of those conditions and simulations, There are several products that come with it. We have a flood extent, which is just like the footprint of where we expect flooding. We have the coincident flood depth or depth of that flooding for that entire footprint. We also have the coincident wave heights, which drive that flooding. And really, to make this more impactful for a lot of our users, those hazards are combined with census data and infrastructure data to translate that into socioeconomic exposure. It's really the impact on people, lives, and the community. Again, all of this data is accessible via easy to use, intuitive web tools. Think of Google Maps. And for the more technical users, it's available for download in GIS or analysis ready formats.
So here we're going to hop through some of our examples of the products we're just putting out right now for some of the Pacific Islands. So Patrick will show you later the extent of the Cosmos products, but we're right now releasing these for the Hawaiian, American Samoan, Guam, and Saipan. And so just want to show you some of these products that are coming out now. So this is Marine Corps Base Hawaii on the Kaneohe Peninsula on the windward side of Oahu. And so here shows flooding for the 20-year storm at current sea level. The ocean is at the bottom of the screen. Kaneohe Bay is in the top right. And what you see is, it's very interesting, is because of wave-driven setup, is actually you get flooding on the right, the top right here around kind of the back side of the airfield and where the marine operations facility is. Now, as we add on a 1/4 meter sea level rise, that flooding, again, it's not on the ocean side, but because of wave-driven water levels pushed into the bay, is now we're getting flooding from the bay side, further extends out across the runway. We start to get into the hangar area here in the top middle. Further flooding with a 1/2 meter sea level rise with a 20-year and with a meter sea level rise. It basically covers the entire airfield, hangar facilities. We get into the Fort Haase area of the beach. Now, we just did this visualization with no storms, you wouldn't see any flooding. So again, these storms provide a more accurate representation of the threat faced by the facilities. Now, this is an open ocean spot. Next, we're showing, this is the Orote Peninsula on the western side of Guam. So we're looking basically eastward into, this is Opera Harbor. The naval part of the facility here is primarily up at the top middle. However, the commercial port, and brings in a lot of the fuel for the power plant that supplies power to a lot of the civilians and contractors off bases here in the top left. And here's the 20-year storm with current. Actually, these projections were just used during during the run up to Super Typhoon Marwar as some of the only projections available for emergency responders. But as we see, with a 1/4 meter sea level rise, a little more flooding here in the top left of the commercial port. Again, potentially affecting material coming in for the civilian population and the DoD contractors. But again, not much here in the base itself. Continued sea level rise, not a lot of flooding in here until we kind of get up to about 1 meter. And again, that's because there's the glass breakwater is one of the largest breakwaters in the Pacific, and it typically gets hit by typhoons. But again, we do start to see some flooding. But again, this points out in the concerns for the Department of Defense, even though their active DoD facilities may not be impacted, the commercial facilities are. And obviously the relationship between Department of Defense and the civilian communities, whether they're civilian contractors working on base or supporting DoD folks when they go off base during off hours. Lastly, we're showing here, this is Hickam Air Force Base and Naval Base Pearl Harbor. So this is on the south side of Oahu. Pearl Harbor is the large embayment here in the left side. Again, you see on the right side, this is Hickam Air Force Base transitions into the Honolulu International Airport. you see here a 20-year storm with 0 sea level rise, you're actually starting to flood a lot of the coastal part of Hickam Air Force Base. As we add more quarter-meter sea level rise, we start to flood almost all of the small aircraft where basically the interceptor fighters are located out here in a lot of these bunker complexes. So we continue, sea level rise continues to go up by a half-meter sea level rise. We're getting into the main airfield and starting to, again, start to flood more of the naval bases units. Actually out here to the right is small arms training range for the Marines also. And with a meter sea level rise to the 20-year storm, basically you see the threat to most all of Hickam and a vast majority of Naval Base Pearl Harbor. So again, as Andy noted, the data are provided in these map packages with layers so that the users themselves can say, okay, I'm concerned about these certain facilities that are in your secure data, secure non-public databases, so you could cross-match those to do your own analyses. But with some follow-on projects that we've done with the Strategic Environmental Research Development Program, we really looked at the ability to generate a range of potentially useful products to support design and siting of new development. And so if there's information on the sensitivity of those structures or those resources, then we can really assess the vulnerability of both the existing development and also help to identify adaptation pathways. So now kind of showing you some of the things that can be done with this kind of information. So here is exposure assessments. So here's showing for plots a percentage of habitats. So these are ecological assets, whether they're shrubs or different types of vegetation. Along the x-axis, again, is sea level rise above present. The y-axis on the left this is what would just be done if we just looked at sea level rise and we didn't take into account flooding. On the right, it's the land cover, that same land cover classes, but flooding during storms. And what you see is for all of these, the curves are much higher up, or much more of these land covers are affected by flooding than on the left when you're just taking into account sea level rise. So again, showing the importance of including this wave-driven flooding during storms to really assess the impact. If we were just using sea level rise, I think we'd underrepresent the hazards being faced. Again, with sensitivity, though, we can really start to look at vulnerability. If we can categorize the physical effects, we can identify really operational characteristics and limits, such as failure modes with fragility relationship to look at disruption or damage states to really identify operational requirements and restrictions. So here in the top right, we're showing this is Naval Base Coronado, where some previous work that Patrick and Andy did, that again we did for CERTIP. This shows a cross-section of a pier, and what they showed is if we have this kind of fragility relationships, if okay, at a certain level of water level, it will cause minor flooding, more sea level or more total water levels will call moderate, and then on to major. And so that we call these kind of plots you're seeing here in the middle depth damage relationships. So when water gets up to a certain point, it creates either minor damage, and there's an operational downtime associated with that. If total water levels get higher, it's a moderate amount of damage, and again, increasing operational downtime. So if we have these depth damage curves, we can really look at vulnerability. So in this case, using the Cosmos model at Naval Base San Diego at Coronado, what we're showing here is a map of a bunch of the docks here. And you see the colors are going from fully operational in green to non-operational in red. And so these are operational impacts to waterfront structures for the 2070s under high sea level rise scenarios. So you see some of them are green, some are orange, or some of them red. And on the right, what we show here is a distribution with time on the x-axis and the different bits of infrastructure, the docks or ramps on the y-axis. And so what we're showing now is a heat map of disruption days above minor, moderate, or major thresholds, and the associated operational impacts of the number of days of downtime that the different facilities would face. So this data basically, if we can get that information on vulnerability, we can start to, or on characteristics of the like depth damage curves, we can now start to look at vulnerability and talk about how that may affect operations. Same thing is if there's something about how those hours of downtime or replacement costs, then all of a sudden we can start to look at potentially costs per decade. And so in this case, along the x-axis is the number of the individual piers. The y-axis is cost per decade associated with either replacement values or moderate or major or the colors. And so this is showing the average decadal replacement costs associated with the exceedance of moderate and major thresholds, again, under the 2070s, under this high sea level rise scenario. So now we can start to actually get to costs, what that will cost. So we can start to think about, you start to think of a benefit cost ratios. Okay, well, there's a threat. How much is it going to cost? But at what point will that cost per decade maybe exceed that? So Patrick will now talk about how these works that we're doing in the Pacific fit in the larger picture.
Thanks, Curt. We've been building out Cosmos now for over a decade, and there's been a lot of fundamental science under the hood. It's been developed both in reef environments and also sandy beach environments. So Curt's been leading that work in the Pacific. And then we've been leading some of that work stateside and developing sort of pilot work in California, where this has been completed now for the majority of the urbanized population. We've also now rolled out products for Cosmos across the Southeast Atlantic. And as Curt noted, we're basically in the process of rolling out the flooding information for all the Pacific Islands. But we also have infrastructure and are building out models and applications and ultimately the products in the Pacific Northwest, Alaska, and also the Gulf Coast as well. And this is all moving toward supporting a common operational procedure for DoD and other agencies that have national interests. And the move is hopefully toward having this information for all of US-based interests and territories within about 5 years or so. However, we're also in a position to support DoD interests globally. So not just the bases themselves, not just beyond the fence line, but also, and not just US, but also beyond looking at DoD global interests. All of our models are based on global wave models and global tide and surge models, which we've run now with the latest suite of global climate models. And so these boundary conditions effectively are available everywhere. And so the model can then be applied and downscaled to DoD interests across the globe. And this again is moving toward this common operational procedure for supporting interests all over, not just so that way when you're conducting your resource assessments, you're not working with different information in different locations, but you're working with the same set of sea level rise scenarios, the same set of storm scenarios, the same set of model results. And so you can easily compare apples to apples and look at the vulnerability of different assets across the globe and then make decisions accordingly of how you're going to allocate your resources to protect those assets. And so the goal here is to provide consistent, sound, cutting edge science to reduce risk, increase resilience, and better direct adaptation efforts, both stateside and abroad. And however we can support DoD in this effort and develop more customized products to support DoD interest, we're happy to do so. And now we're happy to answer any clarifying questions and open up a discussion.
Thank you for the presentation. That was the second time I've heard it. Actually, it was just as good the second time. So I mean, so much to take away from that, and I appreciate the focus on DoD applications and interests. I got one question that I took from Andy's part that I just wanted to lock on to. What gets flooded versus what gets wet? I'm wondering if you could expand on that a bit. That really caught my attention. I imagine it caught others.
Yeah, so we try to use the dynamic wave setup to really be the breaking point or the value at which we discern what gets flooded. So some other methodologies may use total water level, which includes run up, which can be higher, but really you're talking about that swash, that upper level swash that has a very finite volume of water. So it's really like a very transient wet area, whereas we try and determine our flood extent based off what's going to have like a centimeter or an inch of water for at least a minute. So really getting at that impact of flooding versus what might just get splashed. Does that answer your question?
It does. Thank you. That's great. And the impact on the aquifers, and I know from looking over the a handful of the journal articles, you know, the time between the recovery time with an aquifer. I mean, that's critical too. Can you talk about some of that some? I mean, what makes something inhospitable versus just say contaminated or temporarily constrained?
Well, yeah, I'll start off with some of the Pacific Island atoll, but then Patrick can speak more because they've expanded that now to a good part of CONUS. And so what happens is you put salt water over top of fresh water and you salinize it. And so, you know, we can only drink when it's down to, you know, 1 part per thousand, and your seawater is, you know, 34 parts per thousand. And so it contaminates that fresh water. Now, if you have new rainfall, it slowly pushes that salt water out. But the rate at which that happens is dependent on your rainfall. What we've seen currently in much of the tropical Pacific is it takes, you know, a year or 2 or 3 years to push all that salt water out of the freshwater lens. And so if we take our Cosmos annual flooding results and we say, gosh, these areas are getting flooded annually, and it takes more than a year to recover, then we know that that aquifer will not recover. A lot of the future projections in the equatorial tropical Pacific are showing probably decreased rainfall in a lot of cases, so that recovery time may be even greater. Now, listen, there's a number of mechanisms. You know, in 2008, there was a big storm that crossed the North Pacific. Half of the Federated States of Micronesia were overwashed, and they lost all these freshwater resources. The US government filled up clean oil tankers with fresh water and had to deliver it to these places. They could bring in, you know, gasoline or, you know, petroleum powered desalination plants, but all that comes at a cost. So can you do these things? Yes. But what we want to know is hopefully far enough out to, okay, this is going to be a problem at this point. We need to start thinking about what do we do now? Do we somehow figure out how to build desalination? Do we pump fresh water to help accelerate the salt water out of the aquifer, things like that? And so these are some of the ideas being thought about in the tropics. Again, Patrick, if you want to talk about some of the work on CONUS.
Yeah, sure. In CONUS, I mean, productive aquifers are less of a concern. There aren't that many right along the coast. However, the water table is very shallow by nature, just because it's controlled by sea level. And so as sea level rises, that water table rises as well. And so when we were building out this work and focused mostly on coastal flooding, overland flooding, that is, and erosion, the more stakeholders we interacted with, the more we heard about issues with saltwater intrusion in ag, in treatment plant facilities, rusting of infrastructure. And so we recognized the need to develop a groundwater hazard module to look at how that water table is responding to sea level rise as well. And so we've now done that across California and the Southeast Atlantic, showing how that water table responds to sea level rise. And the primary issue there is there's lots of leaching fields with septic attached to septic sinks, for example, and lots of coastal communities and barrier islands, for example, that rely on having some freeboard between the water table and the leaching field. And lots of folks are now seeing dysfunctional leaching fields because of that rise in the water table that's been observed just the last few decades, for example. There's lots of buried pollutants, some of them of which are capped, which were thought to be safe and secure, but now with rising water tables and more so in the future, those pollutants can be liberated and introduced back in the environment and causing lots of issues. And then we've got lots of other infrastructure buried in the shallow ground throughout all these communities across the world, really. I mean, we're talking about fiber optic lines, gas lines, electric lines, you name it, in addition to the water table undermining foundations of roads and structures. And so it is recognized as an issue that we had to respond to. And so now we've developed this approach for looking at how that water table responds to sea level rise as a first order approximation of that hazard to couple the overland flooding, and the erosion hazard work that we do in many locations.
And Patrick, if you might want to comment on the scale of that, like percentage wise, it's it seems in like a lot of places that groundwater hazard is even greater in extent.
That's a good point too. Yeah, we looked at this across California, and the exposure of shallow groundwater to the population and to the assets in California, for example, are almost an order of magnitude greater than the overland flooding. And there's not necessarily a one-to-one relationship between the exposure and impacts, but it certainly calls the attention of us to note that it's at least of comparable importance to understand that water table response and that shallow groundwater hazard compared to overland flooding.
Yeah, wow, incredible. A number of thoughts come into my mind. So I'll run them off. I'll run them off as best I can, but it might be a bit jumpy, but one thing that I want to ask, I want to make sure I ask is, what sort of storm scenarios did you look at? I mean, we often hear with through the media when they're talking about climate change, and we hear it sort of every summer that a hurricane or cyclone was now the highest on record. How are you able to model that in the future? If that continues to escalate in intensity and frequency, you've already touched on frequency, but what about intensity?
Andy, do you want to take a first stab?
Sure. So underneath the hood, right, for different regions, there are different regional considerations. So the way we include storms on the Atlantic coast is different than the way we include storms on the California coast, but ultimately it comes down to we don't model one storm for sure. It's actually, we model many storms, and then our ultimate products are actually a composite of all of those storm simulations. But the number of storm simulations and how we pick is really due to what we see as the nearshore impact. So we're looking at the elevated coastal water levels from that storm. So how intense that storm is to really drive overland flooding. And that's how we pick out the representative storms that we're going to be putting into that simulation bundle. And again, that whole bundle of simulations is then composited into our final product.
Great, thank you.
And so real quick, so you're saying, and just to remind folks that we're using these future global climate models.
Yeah.
So those future storm tracks, those future storm intensities, that's the important thing, is a lot of folks have just taken historic stuff and pushed it up with sea level rise. We're actually using the newest Intergovernmental Panel for Climate Change, AR6, which they call it CMIP, the Coupled Model Intercomparison Project. So all these different international government institutions and academic institutions put these models all up on a website, and they kind of have so you can kind of do a comparison rodeo. And then we don't just use one of those models, we use an ensemble of those, because some of them are, they're tuned to be, I'm making this up, but like, okay, the Europeans is more optimized. They get the Atlantic better than the Pacific, versus maybe the Japanese model gets the Pacific better. And so we're using an ensemble of those to both drive the winds and storm surges. So we're using these future projections that are taking into account of that warmer sea surface temperatures, which can make more intense cyclones, but also potentially more wind shear. So maybe your frequency isn't as much, but when you do have the storms, they are more intense. Their tracks are different. Those are all incorporated into these CMIP-6 models that we're using to push these simulations. So we are taking into account climate change in these projections, not just sea level rise, but the true change in those storm tracks, which are affecting storm surge and waves.
On that note, the sea level rise, the overwash effects, the 1-2 punch of it all. What is there a third punch? Is there a fourth punch? The compoundedness of what you all have talked about. What else is out there that, I hate to be so glass half empty, but are there other are there other things that weren't added to this that could actually make these future forecasts worse?
Well, Patrick, I mean, I think the one of the things in the small tropical islands, it's really wave driven. But when we get to CONUS, it's also a lot more of these bigger storms coming in. And you want to talk about compound flooding, Patrick, and some of the things you've done there.
Yeah, sure. Yeah, I mean, compound flooding is definitely a major area of growth and research and trying to understand the different physical factors that contribute to flooding and anywhere, but along the coast in particular, where you can have this confluence of ocean-based flooding, rainfall-based flooding we call pluvial, and then fluvial flooding as well. And then in urban environments, there's also stormwater related, which is trying to develop stormwater networks, and that sort of flooding is definitely the cutting edge. So it's trying to understand all these different drivers or how you can get flooding in any one location is exceedingly complex, but it's getting better and better. There's also the issue of ground saturation, which is being addressed as well. So we've seen instances where, for example, the 1-year rain event can result in the 100-year flood event if the ground is fully saturated. And so there's all these different factors which the models are getting better and better at capturing, and the scientists are getting a better understanding of how to integrate all these different factors together. So in CONUS in particular, the hurricane-driven flooding is coming from the ocean side and also from the intense rainfall. We've had these events in Harvey and Florence where there's been 30, 40, almost 50 inches of rain in some of these events. And so obviously, if you're ignoring the pluvial aspect of it, you're going to miss a huge component of the flooding. And so in the new work that we did in the Southeast Atlantic, we had to incorporate that aspect of flooding. So that aspect of compound flooding was really important to get it right. In California, the confluence of extreme precipitation and very large waves does not have that strong of a correlation, so it's not as critical. So there we do include fluvial discharge and overland flooding as well, but the pluvial flooding isn't as important. But then as you move further north into some of these other environments where the snow levels are changing dramatically along the coast, such as the Pacific Northwest, and so you're getting more and more precipitation as rainfall as opposed to snow in the future, you're going to have flashier systems. And that's kind of where the science is going, is better understanding of all these compounding factors to really capture that risk, not just from the ocean-based side, but also from rainfall and from river flooding as well.
Mm.
And so if I can add on to that, the other thing that we're starting to really take a look at is that, a lot of the coastal ecosystems provide significant protection. Like you hear about, when a hurricane hits Louisiana, how those marshes absorb a lot of that storm water, or when they hit places like Puerto Rico, how those coral reefs dissipate up to like 90% of that wave energy. And so as those coastal ecosystems degrade, that is also increasing the threat. We showed just that, coral reefs have degraded, up to a meter, have eroded up to a meter in the past 100 years. We made a calculation that if that happened along all the US's 3,000 kilometers of shoreline, that would increase the annual damages by over $1.8 billion. And so then if a 20-year storm event, we're talking multiple billions of dollars. So, that the degradation of those coastal ecosystems, so protecting them, but that also is an opportunity for adaptation. There's been recent executive orders about nature-based solutions just for providing environmental justice, but also for adapting to climate change. And so that's one of the neat things is that, hey, those have degraded, but what is we can restore coastal dunes, coastal wetlands, mangroves, coral reefs that provide a lot of coastal protection. And the neat thing is this is kind of where we're just starting to go with the suites of models is we can, we run these models over the existing seafloor and beaches and coastal dunes and things like that. But what we could do is in the models, we can add, okay, let's double the dune height. Let's restore that coral reef. Let's make those mangroves more denser, rerun the models, that flooding extent narrows. Then we could say in that area where the flooding extent narrowed, we can quantify those buildings or those people in there. And that says that's the benefit of that restoration. Now that's super important, because how does Army Corps of Engineers justify doing anything? Or if on the private sector, FEMA, all through a benefit cost analysis. Well, you have the cost of whatever restoring your dune, then you have the benefit is, hey, we protected these numbers of buildings that have this value. So we're created this modeling system that we can provide that kind of information. As of yesterday, FEMA announced that through their hazard mitigation program, is releasing over $30 million to Puerto Rico to restore their coral reefs to reduce coastal flooding. And so that modeling, the modeling that supported, was based on the Cosmos system, our Cosmos system here. And this is just showing this incredible opportunity, both in the private sector and for Department of Defense, to use these things. So again, like we showed you, hey, with sea level rise, here's this heat map. These docks are going to be affected sooner than others. We can also then put adaptation in there and say, if you want to protect those docks, here's what we need to do. Here's the benefit, whatever your construction costs are, so you can run those through your calculators. So that's again, the degradation of those coastal environment ecosystems is a threat, but we also have this incredible opportunity to use nature to help address some of these needs.
Absolutely. Well, on account of the time, I got one more question, but I wanted to add 3 examples just from my own experience, just to add to the complexity of it all, and where you're not really sure where you're going to get stung by these things. 1997 Hurricane Floyd hits eastern North Carolina, Category 3, I think it was by the time it made landfall. It wasn't that it was so strong, but so big and so slow, and just trudged right through North Carolina, just unloaded on the eastern part of the state. And so I was living in East North Carolina at the time. And, the flood levels raise over time. They don't go down. And so that catches all sorts of people off guard, island towns, that sort of thing. But what I recall the most was the pork industry and the lagoons that they have there, all like ruptured and collapsed as many days after the effect. So you don't know where you're going to get stung. Here in Florida, and in the Bay, just right outside of the MacDill Air Force Base here, a noticeable decline in seagrass levels, and so. That may not be caused by anything that we're talking about here. That just may simply be runoff, pollution, whatever. But that, as you mentioned, Curt, that is eroding the natural absorptive capacity for things. And so we're not necessarily testing that, and yet we're potentially more vulnerable. And then third, I was in East Timor, Timor-Leste 15 years ago plus for a while, and I can remember a story of mangrove collection for firewood, which was at the time, I believe, illegal. And I remember hearing the story about law enforcement going into a troubled village and attempting to impose the rule of law to quickly get chased out, and by the skin of whatever of their chins to get back to the capital, saying, hey, look, we got to use this mangrove wood for our dinner, for getting our dinner tonight. So it just makes the climate change stories at the local level for all of those communities around the world, that's going to be a challenge over time. Okay, now maybe for a glass half full question to end on, Curt, you kind of answered maybe half of it just now, but what are some low cost adaptation measures that can be taken? I'm thinking Pacific Islands, but there's a number of low-lying areas that are going to get hit with these things in places where they can't bail themselves out financially. And so cost-efficient adaptation, an ounce of prevention worth a pound of cure, as the saying goes. Any thoughts on that?
Well, you brought up a great point. They've taken out mangroves for firewood to put in like shrimp ponds and stuff like that. And there's a lot of great work that's already been done on how that increases hazards. So you step back and you let go, mangroves are going to grow. And so you can use local, local materials. Same thing with corals. Neat thing, just to let you know if you weren't aware of, but DARPA, the Defense Advanced Research Projects Agency, people did things like the internet and stealth technology, mRNA vaccines. They actually have a $130 million program called Reef Fence, and that's accelerating both coral reefs and then oyster reefs. The oyster reef test site is off Panama City at Tyndall Air Force Base to basically make nature grow faster to provide more protection. And what we've shown, at least on the coral side, is that restoring coral reefs to reduce coastal flooding is 1/10 the cost of traditional gray infrastructure. And you're going to see the same thing with oysters. And then they also provide those communities, your fisheries, your recreation, tourism, again, keeping those communities in which a base sits, keeping those communities healthy is super important. So those are some of the options. The other thing, the Army Corps of Engineers dredges hundreds of millions of dollars worth of sand, maintain shipping channels, expand port facilities, and usually dumps it offshore. General Spellman, the head of the Army Corps of Engineers, says this engineering nature, like, we got to stop wasting this. And so to rebuild those marshes, to put those back on the beaches, to build those dunes higher, we have this incredible opportunity to better utilize, to better utilize nature in this, again, at lower cost, and we receive all those other benefits. And that, to me, gives me a lot of hope, but I'll let Patrick and Andy answer too.
Fantastic.
Yeah, I mean, studies have been done which show that a dollar invested in adaptation now saves about $6 to $7 in impacts later. So the sooner we act, certainly the better. But we're not going to defend against a meter sea level rise tomorrow. No one can afford to do that. That's been looked at in places like Pacifica, for example, in California. They have lots of issues with coastal erosion and flooding, and the cost to build a wall to defend against sea level rise over the next century is about $2 billion. And we're talking about a community that has a $40 million a year budget. And so it's going to take a stepwise approach, like a trigger-based approach, which lots of people are starting to, an adaptation pathway type of approach where we make incremental changes to help protect ourselves and using a quiver of tools. I mean, green solutions are going to be important in many, many locations, and other areas we're going to have to dig in and defend ourselves. And in other places we're going to have to get out of the way. And it's going to be a range of solutions. And I think the sooner that we have, the robust science basically to support decision-making and acceptance that this is an issue, I think that's where we're sort of at. I think we're almost there, where we're accepting that this is an issue. It's a global issue, and then we can move forward on and arguing about solutions as opposed to the underpinning science. And I think we're almost there. But evidence has shown it takes about half a century to get from the science-based knowledge to transform that into policy and action. I think we're almost there now. So I'm optimistic that we're at a point where we can really start thinking critically about the solutions and not argue about the science.
Right.
Andy, do you have anything to add?
Andy, yeah.
Oh, no, I would just reiterate what Patrick and Curt had already mentioned. And I think one big highlight is that there's not a solution that fits all. There's not one size fits all solutions. And really, it probably won't take one solution for any community, but probably a whole portfolio of approaches. But really underpinning that all is to actually have evidence to at least start the dialogue and start a real, honest dialogue rather than just sticking your head in the sand, for lack of a better metaphor.
Mm-hmm.
And one of the things, going back to the purpose of this Cosmos effort that Patrick started a decade and a half ago, is to provide this consistently everywhere the same suite. Because what we've typically seen is, I always say this, Professor Sarah does this project here and consultant Bob does a project there, but it's always an apples to oranges. By providing this consistent suite across the entire nation and potentially internationally, what it allows for is prioritization. Because as Patrick noted and Andy noted, we don't have enough money to solve all the problems right now. We need to know that we have to do triage, that this is critical. We have to address this in the next 5 or 10 years. okay, this one's, out on our 30 or 40-year planning horizon. Gosh, we can push this one off down. But we really need those consistent products to allow prioritization so that we can attack it in pieces, because we can't do it all at once. And so what we hope is this, this consistent sound suite of products, starts to allow Department of Defense, the rest of our federal family, states and territories, and again, some of our international colleagues to be able to start to do that, because that's really it is to prioritize so we can basically save lives and dollars.
Right. Well, those are some great ending points there. My 2 cents add to it all is one of the things I work at the university, the Joint Interagency, Intergovernmental, Multinational, and Commercial Network capacity. The JIMC, as the Department of Defense calls it, but it's easy to sort of grasp at first, but far more complicated when you get out in the field, when you actually try and connect those dominoes. But ultimately, you take Andy's observation that, it's not one size fits all. It's going to be different in every place. The cost implications that you mentioned, Curt, it's going to have to be locally derived. So, how do we then work this through the networks that we have so that this can be a shared response? I mean, the more that we get out the checkbooks, it's not going to work that way. We're going to have to redefine that. So let me offer you all any closing thoughts. I mean, this has just been such pioneering work on your behalf with so much implication. Any final thoughts?
Yeah, I would just say it's all an effort toward co-production and developing products that can support the different agencies throughout the federal government and beyond. So we're always looking for feedback from DoD and other partners and stakeholders of what kind of information do they need to make decisions. And we have a lot of data that we basically don't use in some ways. We sort of distill everything to create this seamless set of products, but there's lots more information that could be provided to support various regulatory issues or thresholds of risk that bases are trying to avoid. So the more feedback we get, the better the product can be developed and hopefully support action moving forward.
Yeah, thank you, Patrick. Well, I mean, there will be some significant follow-up to this. I can assure you all of that. At JSOU, we'll put some links in the YouTube site so that people will be able to access your work and follow up accordingly. And we will keep a close pulse on this as this moves forward, and we look forward to working with you all in the future and the networks that you already have. So I thank you for your time. We thank you for your time, and congratulations on this outstanding work and for this presentation you gave us today.
Thank you for the opportunity.
Thank you.